Perfect. Okay, so let's begin. Jiri, over to you.
Okay, yeah. So hello, everyone. So thank you very much, first of all, to the organizers. I very much regret that I haven't seen this seminar series before because I saw there is like a fantastic lineup of speakers. And all right, so today I'll be talking about disorder enhanced quantum many-body scar in Hilbert hypercube. So this is based essentially on a series of works which initiated in collaboration with Igor and Antoine Beauvais, motivated by their experiments in Rydberg gases. And most of the talk will be probably devoted to this last paper, and there I have to thank my collaborators on this last paper, which is Bart van Vorden, a PhD student who just finished, Matteo Marcuzzi, you might very well know, and Karelian Schoutens, who's also from Amsterdam. So the ingredients we will need for this talk are Rydberg lattice gases, which can be operated either under blockade or facilitation condition. And most importantly, I will be discussing the role of disorder in these systems. And then we will see how this can be exploited to different applications, such as excitation transport, or how can one engineer synthetic lattices, and more finally, I'll talk about many-body scars. So let's start. So Rydberg lattice gases, as the name suggests, are Rydberg atoms put on lattice. Now, just one quick slide about very striking and beautiful developments, experimental developments, which has stimulated lots of progress on also on the theory side. So since 2016, where people started to realize like the first arbitrary patterns using optical tweezers, through creation of arbitrary 3D patterns up to like today's essentially records, as far as I know, in terms of number of qubits on a single processors, which are like reaching hundreds. Now, in case someone doesn't know, so Rydberg atoms are atoms excited to very high principal quantum number, so that you have like large electronic clouds which are interacting together, and this like gives rise to like strong interaction between these atoms, which typically can be of two types depending on the regime in which you are, which are either dipolar interactions, which decay as a power law like 1 over r cube, or van der Waals, which go like it's a faster decay 1 over r6. But they are algebraic in any way, and this has been exploited, since like decades now, to various tasks, including quantum information processing. Obviously, like Rydberg atoms are, one of the forerunners for like quantum computing. For us, what will be probably most interesting are quantum simulators of condensed matter system, or you can use their high sensitivity to electric fields, for instance, to do like quantum enhanced metrology. More specifically, so this is there is like nice like recent review by Antoine Beauvais and Thierry Lai. So the ingredients we will need: the typical Hamiltonian you will encounter in the literature, or the two Hamiltonians are these two ones. So this is one which like contains the spin flip interaction, which is typically the dipole-dipole Hamiltonian, and this so here the sigmas are between two Rydberg states. What we will be concerned in this talk is the other one, which is the van der Waals interaction, which features this density-density interaction between two atoms which are put in a Rydberg state. So just very briefly, again, the same Hamiltonian. So this consists of a spin flip, which is your laser driving field at some radio frequency, chemical potential, and interaction, which is long range. And side remark, the nice thing is also it can be made either repulsive or attractive. So throughout the talk, I'll be considering repulsive interaction. And again, like the most common probably regime in which these gases are operated is so-called blockade mechanism, which simply means that if I put one atom excited, it will shift out of resonance like a neighboring atoms, which will prevent its excitation. And this has, of course, many applications, performing quantum gates, etc. And to this audience, the probably like most up-to-date or like most interesting application is it is behind or it corresponds to the effective description by what is now known as a PXP model. The other regime, which is probably a bit less known, is like a facilitation mechanism. So in some sense, it's opposite of the blockade. And it's based on the fact that if you put your detuning or you set up your detuning such that you actually are on resonance with the atom, which is a neighbor to an already excited one, you will facilitate the excitation of these neighbors. And here, just a snapshot from a paper by Igor and Juan. So, okay, this facilitation mechanism can also lead to all sorts of like nice physics, such as aggregate dynamics. So, for example, here I have like initially few seeds, and as the time goes on, due to the facilitation, so these little like clunks of excited atoms, they are growing in time. Okay, very good. So the next ingredient we will need is position disorder. This is something which has been somehow neglected or, well, not really considered until relatively recently. And the story is as follows. So again, what we have in mind typically is like the experimental setups people are using, which means atoms in optical tweezers. And the point is that here the atoms typically they have finite temperature. And this means that their position, so typically if I take a lattice gas, I parameterize the position of my atoms. Okay, well, typically I consider them to be sitting at some equilibrium positions. However, in principle, they can fluctuate around these positions. And these fluctuations in positions, they lead to obviously fluctuation in the interaction energy because it is distance dependent. Now, typically, the description we employ is we take the tweezer potentials in a harmonic approximation, which leads to a Gaussian distribution in atomic positions, where like the width of the spread of the atomic clouds is proportional to the temperature, as one might expect, and inversely proportional to the trapping frequency squared. And also, well, what we will later take into account is the actual shape of the tweezer trapping potentials, which is they are typically isotropic, like in a plane, like perpendicular to the tweezer axis, and the trapping is more loose along the direction of the tweezers. So now a few words about the properties of the disorder. As was like apparent from the previous slide, so the atomic positions are drawn from independent like distributions, which means that the positions are independent, but not their distances, right? So if I draw, let's say, 3 atomic positions at random, so let's say the distance between first and second D1 is random. Say the second distance D2 will be random as well. But if I fix D1, D2, D3 is not random anymore, right? Because it depends on these ones. So this feature, it leads, I mean, it has several consequences. For instance, it leads to asymmetric energy disorder, and the distribution for the energies, which is written down here, it's a fat-tail distribution with no defined momenta. Now, this is a bit peculiar, but it's easily understandable, because if I take like 2 atoms from a Gaussian distribution, they have non-zero probability that they will come arbitrarily close to each other. And of course, for like algebraic power law interaction, if they are like arbitrarily close to each other, the interaction energy will diverge. So this is more of a like mathematical artifact coming from the Gaussian distribution of positions. It is good to know. It doesn't have, I mean, it is not something you would expect experimentally. And typically for like reasonable experimental parameters in the numerics, it also doesn't really pose a problem. So it's really just like, say, mathematical feature. I will comment on this also in a bit. So Okay, comes the question how the disorder affects the atomic dynamics. And again, so this is something which came about from the discussion with the group of Antoine Brevet, where they observed the following. So let's first consider a very elementary example of two atoms. If I drive my two atoms, let's say in the blockaded regime, and such that I set up my the tunings and Rabi frequency that I am driving, I'm coherently connecting these configurations up, down, and down, up. And I avoid actually driving these two states through the up, up configuration. What I will see are some sort of like kind of coherent oscillations. Now, if I, on the other hand, put myself in the facilitated regime, so I'm driving again these two states through the excited state, up, up. What will happen, or what happened actually in the experiment, you see very clearly the suppression of these like coherent oscillations. Now, in order to understand this a little bit better, other than just saying, okay, fine, it's due to disorder, one can like do a little bit of, let's say, development. And what we did, we can, you can postulate these two assumptions. So first we work under the facilitation condition. So this one here, so the detuning is minus nearest neighbor interaction. And as is also often the case, the nearest neighbor interaction is the dominant energy scale. Here, meaning it's larger than the driving Rabi frequency and the disorder. Now, under these conditions, you can go from the parent Rydberg Hamiltonian to formulate an effective Hamiltonian, which is written here. And okay, essentially the content of the Hamiltonian is the following. It conserves the number of clusters, where cluster is a sequence of consecutive spin excitations. And it also has a property that, okay, or in other words, it also means that if I have, for example, two clusters, so they can grow or shrink, but when they come close to each other, they will always remain separated by a downspin. And this is like a clear prescription how actually to think about, let's say, your Hilbert space. And this is shown here on this picture here on the example of three atoms. So this is like the full Hilbert space with spin configurations at given energy. And when we substitute for this delta the facilitation condition and take into account this separation or the fact that the number of clusters is conserved, so the Hilbert space will actually have this structure. So it will be separate into blocks labeled by the spin cluster number. Okay, so what is also, sorry, if I go back to this slide, so what is also clear here, well, okay, some features are not apparent because it's like very small system, but already here you can kind of see some structure emerging, right? So this is a situation for one cluster, and if you look at it, this is like a nice planar structure with like a square lattice kind of underlying geometry. So this is indeed the case. You can extend the analysis like beyond one cluster. And what you will find out that the structure of the Hilbert space indeed corresponds to a hypercubic lattice, where the dimension of the lattice is given by 2 times the number of clusters. And due to the simplicity of this structure, it also invites you to think about the many-body dynamics as essentially a dynamics of like a particle hopping on your Hilbert space graph. So, for example, since we talk about disorder and the related like localization phenomena, so you can think about this as Anderson localization on your Hilbert space graph. So here is a snapshot of how actually look your eigenstates as organized according to their energy. and inverse participation ratio. So here you have some relatively strongly localized states. Here is a snapshot of delocalized state, and here we will also be talking about this in more detail, is some rather special state, which is sitting only on the edge of the Hilbert space. Now, if we go back to the experiment.
Sorry, can I ask a quick question?
Yeah,
so
sure,
for these
sure.
things on the top right, when you plot the eigenstates, how are these results? Because I understand, if I understand correctly, what you're saying is that they're actually exponentially localized in Hilbert space. And how did you obtain this result? Is the question. How do
you mean this result here?
Yeah, I mean, how is it known, for example, that they're like this? For instance, how is it known that the leftmost sort of eigenstate that you plot, which says Fock localized, how do you know it's exponentially localized is the question?
It's a good question. I don't think we did some in-depth analysis of not in this scenario. So we did similar analysis of the envelope of this eigenstate in slightly different regime. But
let me tell you why I ask a question.
Yeah.
Let me tell you why I ask a question. So, because the disorder that you have might be uncorrelated or correlated in real space, but even if it is uncorrelated in real space, as you probably know, on this lattice, it's actually correlated on the Hilbert space lattice. On this hypercube. Right. So, I mean, as far as I know, certainly if you do a calculation like you're doing for what's called the quantum random energy model, which is, uncorrelated disorder in Hilbert space and unconstrained hopping, or you can even constrain it, then you can get exponential localization in Hilbert space. I'm not aware, which doesn't mean they don't exist, but I'm not aware of examples where you have correlated disorder in Hilbert space coming from local disorder in real space, where you get exponential localization in Hilbert space, as opposed to some kind of multifractal behavior. I mean, anyway, that was just a question. If this is not important for the rest of your talk, I'll just
okay. So
later.
Thanks a lot for the comments. So maybe just very quick comments, which I will probably also mention later. So here, in general, so everything is always correlated disorder, precisely because of the fact I just mentioned that we have independent positions, but the energies are always correlated. So this is one comment. The other comment here for this specific plot, we did not study the question you mentioned because this wasn't the main focus. So, but thanks a lot for the comment. So here I'm not claiming they are exponentially localized, but localized. These terms localized or delocalized is essentially just referring to the inverse participation ratio, right? So, but it's not a statement about the envelope or the shape of the localization, whether it's exponential or something different.
No, but the statement then is that, if I understand correctly, that this inverse participation ratio corresponds to a state with finite extent in Hilbert space. So either exponentially localized.
Yes, that's correct. Yes, precisely. This is how it's defined. Yeah.
How is this known? Because it's very difficult to get this to actually happen, even with uncorrelated disorder in a real space.
Okay. So this picture is just numerics, and right. So
okay. So you do exact analyzation, and it really happens.
Yeah. So this was just to see a little bit what these states look like, and right. So you expect your inverse IPR to be between some lower bound and 1. And for 1 is the maximally delocalized, and So that's
thank you.
Okay. Thanks for the reminder. All right. So now going back to the experiment. So actually, the thing which triggered this whole let's say work was the observation that when I make a quench experiment in a chain of atoms with one atom excited, naively one might expect ballistic propagation, but what actually the Paris group observed was a picture here, so which is essentially completely inhibited propagation. And okay, now we understand why even quantitatively. And this is a comparison, for example, between the full theory, which is just again just exact diagonalization or exact time evolution, and the effective model. So here you can see some finer feature which corresponds to this like a nearest neighbor energy scale, which is not present in the effective model. But the correspondence is actually relatively nice. It might not be so obvious from these density plots, but when you actually compare, let's say, the spread of these excitation quantitatively, it also matches nicely. Well, it has to, because it's an effective model. So in its regime of validity, it just has to work. All right. So far for the effect of disorder. Now you can develop this program, let's say, further, which we did briefly, like in this paper here, and we have supplemented. So previously we had this like hierarchy. You always exploit hierarchy of energy scales, and previously the hierarchy we had was the nearest neighbor interaction is much larger than like the Rabi frequency and disorder. Here we want to be even more stringent, and we also require that even the next to nearest neighbor interaction energy is larger than these two. What it means that now not only the number of spin classes, excitation clusters is conserved, but also the number of triples. And we also want to move from 1D to slightly beyond 1D. So this is like, okay, it's still quasi 1D, but it's, let's say, 2D in real space. So we have this ladder geometry. And now if you do the same exercise and you actually like look what your Hilbert space look like, you actually will find the following structure. So these spin configurations are connected in this way. And for example, so we have always like a pair of upspins connected to like a single upspin, which is then connected to a pair of upspins and so on and so forth. And so in the specific example of this ladder geometry, this is nothing but a Lieb lattice. So it's a Lieb lattice, if you wish, in synthetic dimensions. So this is nice. And this is like a possibility to engineer such synthetic lattices, not only, of course, on ladder geometry, but you can imagine like other real space configurations, which then are translated in this like Lieb lattice kind of structure. And as you know, so the Lieb lattices, they feature flat bands. So then again, you can ask the question, what happens to the excitation dynamics in such a system? And
excuse me?
Yes.
So why do you call this a one-dimensional Lieb lattice?
It's so because, okay, this is my unit cell, and I can like get my lattice by replicating this unit cell only along one direction. So yeah.
Okay, thanks.
Yeah, it's just question of terminology, I think. But as far as I know, so any ladder is considered as a quasi 1D system. So yeah. Okay. Right. So we have these Lieb lattices with a flat band, and very briefly, so since flat bands have like a zero group velocity dispersion relation, so the dispersion for flat bands is zero group velocity, so you get localized eigenstates even without disorder. And again, the question one can formulate: what happens to like suitably chosen initial state when you add up disorder? And this is what is shown here. So this is like a snapshot of a time evolution starting from some initial state. And here there are like plots of a variance of like the spread in real space of your excitations along the length of the ladder for 3 different times as a function of disorder. So in the situation with 0 disorder, you are perfectly localized. However, as you turn on your disorder, you will actually at first become delocalized before you become localized again because of strong disorder. And this like delocalization induced by disorder, or well, like this like initial delocalization is indeed like induced by disorder because it leads to hybridization between the flat band and the dispersive bands, which is something which has been like discussed, for instance, like in this paper here. So, okay, this is like a nice, if you want, quantum simulator of this kind of physics. Now, let me spend one slide. So here I would just maybe like to pass one takeaway message, which is that Rydberg lattice gases are actually like a true spin boson systems, because I also think I'm talking probably to community where people are mainly interested in spin systems, but like spin boson systems are maybe slightly less exploited in this respect. And this is like one platform, like natural platform, where you know, these things appear. And this has been also exploited to some extent by Igor, who I think is also in the audience. And you can do like very nice things by you know, looking what phonons do for you. And for example, it led to the design of ultrafast Rydberg state-mediated quantum gates. For ions, you can engineer polaronic quasiparticles, or for instance, engineer three-body interactions. So you essentially, like your small fluctuations, you can write them as a real like bosonic, you can expand them in the bosonic modes, and then in the limit of like small phonon number, you can integrate the bosonic modes out, and you end up effectively with three-body interaction. This is like a picture from like their paper showing a phase diagram you would obtain with such a three-body interaction. So I think it, okay, gives you a few nice openings. So let's move on. And here I have another slide, which will, okay, it's, let's say, not maybe directly relevant to the rest of the talk, but I thought it's more of a, let's say, informal comment on graph theory approaches encountered in quantum many-body systems. There have been few. Also, I've seen that there was a talk, for instance, by Adam Smith, you know, exploiting some of, let's say, graph theory tools to characterize like a many-body system. But if you go a little bit through the literature, I think it's not a mainstream approach for sure to many-body dynamics. But like a few things you might encounter is something I call like naive approach, which is simply that in a given basis, for a discrete system, your Hamiltonian is just an adjacency matrix. And here I borrowed a picture from Achilles and sorry, forgot the first name, Roy, from their paper. So really you just draw what we have seen on the previous slides, your Hilbert space as simply a graph of your like Hamiltonian. Then there are other approaches which are also interesting. For instance, there is algebraic approach, which in which the like graph you are drawing is encoding like the algebraic properties of the elements of your Hamiltonian. So yeah, so if your Hamiltonian is given by sum of some string of spin operators, let's say, so then you can construct graphs, and by applying some nice methods, you can actually make a statement whether your Hamiltonian can be or corresponds to free fermionic Hamiltonians. So this was like done in a series of work by Stephen Flemia. Then there is other approach, which is like taking so-called factor graphs, and they are applying this to actually study operator growth. So it's mainly papers or series of papers by Andrew Lucas and probably some other ones. So okay, here I will stick to what we have seen, so to the naive approach, which is probably not like very generic, but for our specific like in our specific case, it works very nicely. Okay, so coming to the main topic of the talk, which are like many-body scars. So I don't need to present, I think, many-body scar to this audience. But maybe I just would like to put two things on one slide. So there is a lot of talking, of course, due to Zlatko and okay, the experiment by Michel Lukin about many-body scars. As has been described in this like original paper by Chris Turner and Zlatko and co-workers, if you make a quench in a chain of Rydberg atoms, here it's in the blockaded regime from some product state. Surprisingly, you will actually see like not thermalizing time evolution. So in this case, persistent oscillations. And okay, so since this observation, there have been some developments in quotations, which means like order of 400 papers. Like somehow, if we go to the core of how people usually understand quantum many-body scars, is that there is some spectrum generating algebra or dynamical symmetries behind, which can be realized either exactly or approximately, which means that if I am able to identify a charge Q, which has this property for some, let's say, frequency omega, and I can I cook up a state which I can define as sort of a coherent state with respect to this charge acting on some reference state. Then I'll get my tower of states, and like one-line computation for the Loch-Schmidt amplitude gives you exactly like perfect revivals with the frequency of omega. So okay, that's kind of the mantra, let's say, behind many-body scars. Now the name comes obviously from some historical works on single particle scars, which in turn got their inspiration from like ergodic or non-ergodic behavior in classical billiards. So okay, in '84, Heller asked the question, okay, what happens if we consider like quantum wave functions in such a like stadium-shaped potentials? And when he searched through like the eigenstates, he discovered these like scars, single particle scars. And the game, which is typically being played here, is okay, let's initialize a Gaussian wave packet with a defined initial like position and momentum, and let's track its time evolution. And okay, again here it's done again with the help of the Loch-Schmidt amplitude. And here, okay, you will see some pattern, okay, not a perfect revival necessarily, but nevertheless some kind of, let's say, periodicity. So going back to our like facilitated model, as you can imagine, what we will be attempting here is to consider like this many-body problem simply as a single particle problem on our Hilbert space graph. And once again, just a reminder, so we have this effective Hamiltonian, the Hilbert space structure, which is labeled by a number of clusters. And okay, so the dimension of the underlying hypercubic lattice is proportional to the number of clusters. Nevertheless, we will be here really focusing on the simplest non-trivial example, which is just one cluster. And in order to contrast it, for instance, with the PXP model, as I said earlier, this is probably not a very generic approach, because here we are really exploiting the simplicity of the Hilbert space. So this is like a picture of the Hilbert space graph of the PXP model. So I do apologize, there is much nicer picture you know, in Zlatko's paper, for example. This is our own drawing, but nevertheless, it makes the point that here you have some, in general, complicated non-planar structure. So let's analyze this problem a little bit in more detail. Let's break this Hamiltonian in the sum of three terms. So one is just the hopping term, which would be this like spin flip. Then we will have a potential term and disorder. So for us, the potential term will be this next to nearest neighbor, and disorder will be like a fluctuation. So okay, disorder will be like the nearest neighbor kind of fluctuations. So here is the same drawing as we had before, just like rotate it a little bit. And from now on, we just think about it as really like a discrete lattice in a two-dimensional space. And let's first have a look at the dynamics generated by this H naught. So you can diagonalize this H naught exactly. It's actually like a cute problem because this structure, this like a square lattice, which is embedded in this like triangular shaped Hilbert space, you can actually complete it by affixes sides to like 2D or like a square square-shaped potential, and then you can find your eigenstates as a solution to a two-dimensional infinite potential well with extra conditions that you require your wave function to be zero, not only at the boundaries, but also on the diagonal. When you do this, you will find what you are looking for, so the set of your eigenenergies and wave functions. And if you look at the structure of the wave functions, you will find one nice thing, which is that in the sector of zero energy states, which are which have degeneracy given by the actually linear size of your lattice or of your chain. So these zero energy states, if you plot them, they clearly correspond to what you would call a scar, in a real space. So this is nice. So now let's keep this analogy with single particle scars. Let's carry on further, and let's play the same game. And by same game, what we mean is let's make a quench from initial Gaussian state. So here it's Gaussian in quotations because, it's defined on the discrete lattice, and also motivated by, let's say, experimental feasibility. What we do, we actually project like the Gaussian state, which, in principle has support on all of states, or like all of the basis states. So we project it on only 4 basis states with the highest weight. And then what we do, we monitor the dynamics using time average occupation of the basis state. So this is like, well, it's not Logarithmic amplitude, but it's projecting the time evolved wave function like with respect to given basis states, and we time average. And this also is nice because this is typically what you would have as experimental probe just by monitoring the probabilities of individual spins being up or down. And so what you get from this is, so this is this time averaged occupation of the basis states. And so this is like one picture for initial states starting from the tip of the triangle. So this is like a zoom, if you want, on our effective Gaussian state. So you can see what we have here. We have like the highest weight is really just one basis state, and then we have like its neighbors. And we specify the momentum that we give it like effectively a kick along this diagonal direction in the Hilbert space. And indeed, what you can observe is that, here very manifestly, you have this like single particle scar. Similarly, it's like a similar situation, but, instead our initial state is sitting, like at this place, and we give like a kick along the direction. So again, this averaged occupation of the basis state clearly reveals this like scar behavior. Okay, so now, of course, the question is, what is the effect of potential and disorder? So let's start with potential. Okay, this is just the definition, but what it simply means. So, as I said previously, the potential is essentially the energy of, or counting how many next to nearest neighbors you have. And as you can see, so along this baseline, there is only one spin, so the potential energy is 0. Along the second, baseline, you only have 2 nearest neighbors, so 0 next to nearest neighbor, so it's 0. And then you go up linearly as you are going deeper in the triangle. So it is nothing but like a characteristic staircase structure. Okay, the disorder is more interesting. So here are a few comments to make. So actually, I don't think maybe I'm wrong, but the main point, you know, since we want actually to have a look at things like, you know, log amplitude or something like that, or we want to average over time, what we actually want to consider is explicitly time-dependent disorder, where the positions of the atoms depend on time. And for this, so our initial state will be, okay, some initial state of the spin, so let's say the Gaussian state, but then we also need to specify the initial state of the atoms. And for this, we typically would take like a thermal state corresponding, okay, to some experimental parameters, to some temperature. Next assumption is also, okay, there are a few, like it's more of technical details, which are maybe not so exciting, but we also assume typically in experiment, you would only have like ground state atoms, which are trapped. So we assume that the Rydberg states are actually also trapped with the same trapping potentials. This is not something which is yet available, but there are some experimental developments along these lines. So let's hope it eventually will happen. And the most important comment here probably is that if you want to treat the full like spin boson model quantum mechanically, this is actually a quite difficult problem. And I don't know of some, like, there are methods, let's say some numerical methods, some MPS-based approaches and so on, but the problems are the bosons, right? Because if you have some high occupation number, with exact diagonalization, you will not go far because, you know, like the dimension of the bosonic space will be just large. So it is actually a difficult problem, and we are playing at this moment with some variational approaches. And if someone in the audience has experience with that, I would be very, very happy maybe after the talk to hear more. Nevertheless, for the purpose of this paper, because of this complication, we simply treat the atom motion as independent classical harmonic oscillator, which leads to time-dependent Hamiltonian, and which actually is a reasonable approximation, which you can control to some extent. Again, I will comment on this a bit later. So here, the disorder, you can write it down. As I said previously, this leads to like distribution of energies with undefined momenta. However, when you make the harmonic approximation, you know, things becomes simple and especially computable. So I will not have time in this talk, but okay, this allowed us to make some further analysis of this problem to, you know, be able to compute like expectation values of interaction energies and so on. Sorry, can you still hear me? Because yeah, okay, good. Sorry, thanks. Because sometimes the internet connection goes off. So yeah, thanks. Okay, again, we saw this picture. So for the time remaining, bear with me. So you know, in the following, what we call D, so epsilon is something parameterizing the anisotropy of the trig potential, and D is a number, but for us D is the strength of the disorder. And as I said, we treat the atom as classical harmonic oscillators, which okay are like it's like simple harmonic motion where the amplitude and the like initial position of your atom are given in terms, okay, so in terms of initial position and initial momentum, and both of initial like position and momentum, we take them from we draw them from a Boltzmann distribution. So this like specifies our disorder. And okay, so what is the effect on scar behavior? So first of all, again, in analogy to single particle scarring, so this is like a snapshot of log-Schmidt amplitude. So you know, you have like after the initial drop, you have some like wobbles, and here what we do, we choose our like averaging window. Okay, in principle, you should check whether your result depend or how much it depends on the choice of your averaging window. And we also make sure, this is a bit of technicality, but that the window over which we average is smaller than a critical time, which is some estimate we made for which you know, this approximation of your atomic motion in terms of independent classical oscillators is valid. So okay. So this is again like a picture for a quench from, you know, this initial Gaussian state launched along the main diagonal of the triangle. And in order to quantify things a bit further, what we introduce is some fidelity, what we call, okay, it's not exactly fidelity, is a quantity, but like it's designed in a way that it describes like the resemblance or overlap of like your scarring behavior you would get by looking at the average occupation of the basis states, how much it resembles to like a perfect scar, which is the one you will get with only hopping on your lattice. So it's a lattice with no potential, with no disorder. So this quantity, when it's 1, it means that you have perfect overlap with this picture. And when it's 0, so it means that you will get no scarring behavior at all, in the sense that you know, you would get like uniform featureless distribution on your basis states. Very good. So how does it look like? So here is a picture on how things depend on the disorder. To have some notion of, let's say, integrable, non-integrable, what we do, we also plot a level statistics of the full model as a function of disorder, where you know, here these two dashed lines are like integrable, so corresponding to Poisson or Wigner-Dyson distribution. And here are the snapshots of our averaged occupation, time average occupations. For no disorder, somewhere what looks like fairly non-integrable like regime, and a limit for a strong disorder. And what you can see on these 3 pictures that okay, there is like clearly a dependence on the disorder. One comment is that this picture is no disorder. So the only difference between this picture here and here, well, apart from the fact that it's for different system sizes, but the only difference is really the presence of the potential. So here you can see already what the potential is doing in terms of let's say, scarring behavior. But most importantly, so if you look at this quantity, this quality of like scarring, you can see this you know, clear peak as you ramp up the disorder. So this can be interpreted as scar enhancement due to disorder. And the interpretation, okay, I can say more about it, but it's not relevant for now. But so our interpretation is simply that you know, initially, as you ramp up the disorder, so you force your initial state to have overlap with states which are essentially kind of localized along your scars, and this enhances this overlap with the scar state. So
can I ask quickly about this?
Yeah.
Has anything like this enhancement been seen in a stadium billiard?
It's a good question. I'm thinking, so maybe you can help me, but I'm thinking what would be the role of disorder, yeah? Because here the disorder is something we have on top of the usual stadium billiard setting.
Yeah, I mean, I have no idea because I've never seen people studying billiards with scars as well as disorder. That's why.
Correct. Yeah, we didn't. Okay, so we went through a bunch of these historical papers you discovered for us, right? So Heller and coworkers and Kaplan and etc. But I don't have a memory of any paper talking about disorder indeed. So I don't know. Yeah, thanks. Mm-hmm. So yeah, so that's like one thing. The next thing, which we'll try to be fast now, is what about normalization? So here again, what we did, we considered like a quench from a series of initial, so a bunch of initial quantum states. And then we looked at second Rayleigh entanglement entropy of the half chain. And the states we considered, so once again, like a Gaussian state, but then to have some to be able to compare it to like other settings, we also considered like mid-spectrum eigenstate, which, here mid-spectrum eigenstate refers to a half chain, because what we want initially to have like 0 entanglement entropy. And similarly for a random state. So it's like a just state, like a random superposition of basis states from a uniform distribution. And what we see here is, it's a little bit of wishful thinking, but so this is like a time evolution on a log scale, also like scaled with the size of the system, but you have some initial rise in entanglement entropy, and then, one should zoom in this region here, which looks like let's say we call like a slow growth for all considered states. This might be a bit of surprise because you might say, well, I might have like slow growth for my Gaussian state line because this is a state which I really like launch along the scar. However, for these states which are like random superposition of all states, I also get slow growth. And like interpretation of this might be the fact that actually what we call like superscaring, which simply means that actually in this simple picture, here this is a picture of 2 such scars, but if you actually plot all of them, they will actually fill like almost all space. So there is exactly, I think, m of them, plus minus 1, don't remember. But it means that each basis state either belongs to a scar or is just like adjacent to it. So no matter what like initial state you cook up, you will always have overlap with these scars. So that's it. Another comment is if we look at standard deviation of the saturated entropy, which people also like often consider, let's say, in the studies of MBL. So you see this typical peak when you go first into this non-integrable regime, and then for strong disorder, you go to some integrable regime. But an interesting feature that this enhancement is quantified by this like fidelity of scars, if you want. It happens somewhere here, yeah. So for d equals 0.12. And it is something you don't really see in the saturated entropy. So it seems to be something like a bit different. Very good. Now, this is actually a picture from the supplemental material of the paper, but I find it perhaps even more interesting. And this is like, another, I think, takeaway message. And it's the following. So let's here focus, it's maybe not very well visible, but let's focus on these 3 curves. Here. So it's all of them are quenches from our Gaussian state. This brown line is like in the case where we only have nearest neighbor hopping and potential, so no disorder. But then we have these 2 other lines. So one is with static disorder. So this is exactly the scenario which, as far as I know, is typically considered in most studies. And here the blue line is the same thing, but with the time-dependent disorder. And here you can really see very clearly the slow growth of entanglement entropy, which is very different qualitatively from when you take a time-dependent disorder. So in other words, the realistic atom motion has a significant effect on how your thermalization happens. Again, this is a simulation where all the atoms are just classical oscillators. So, it's an open question. Okay, I have my guess, but what actually will happen when you can really solve for the quantum dynamics? But the clear message is that, the motion really has an effect as compared to static disorder. Final and last thing, also relatively quickly, the facilitated Hamiltonian, you can actually map it to a Heisenberg chain. And you can do it through identification of the domain walls. So remember, so we have like these clusters of spin excitation, So the end of the cluster defines a domain wall. So let's call a domain or spin configuration up 0 and spin configuration up down, which is actually our domain wall 1. Okay, there are some technical subtleties, but at the end of the day, you can make the following identification done actually by Matteo Marcuzzi. So you can map your Rydberg spins to Heisenberg spins. And this actually results in a map between the spin flip Hamiltonian. So in the language of our, it's just a real space hopping. So this actually corresponds to a spin half XX Heisenberg chain. And indeed, also as a comment to a question by Achilles, is the disorder here also is still highly non-local, in this Heisenberg chain. Now, second part of the story is following these results by Hoshi Katsura and co-workers. Based on Onsager algebra, okay, so their work was inspired by some work of Paul Fendley on clock models and so on. What they did, so they proposed okay, bunch of clock, let's say Hamiltonians and charges written in this form, such that if you cook up your coherent state as your state as some kind of coherent state, acting with this charge on spin down, what you will get is when you look at your log-Schmidt amplitude, nice revival. So these are, if you want, your clock states. Now, the comment is that the simplest instance of this construction is nothing but exactly XX Heisenberg chain. So here we have really a very explicit mapping between the facilitated Rydberg model and instance of these Onsager scars. And if we zoom a little bit closer, again, let's use once again the simple structure of our Hilbert space. So here we just write down more explicitly this Onsager scar. So we just expand the exponential. So we have all the powers of our charge, and this picture here would correspond to the sector where I act only with a single charge. And the important point here is when we actually look at the structure of the charge, it only creates a pair of adjacent excitation. So here the full Hilbert space, you have pair of excitations all over the place, but only so the adjacent excitations are sitting only at the edge of the Hilbert space. And this allows us to indeed identify the projected, one should say, Onsager scar as a state or sitting on the edge of the Hilbert space, which is exactly like our single particle scar. This also allows to push this analogy or this comparison between what we did and what the Onsager scars are. So for example, they did some extra effort to engineer integrability-breaking disorder, which breaks integrability but preserves the scars. So they use some MPS to gain some insights and so on. But nevertheless, so at the end, so they proposed, for instance, this perturbation. And here you can go, term by term and to actually look what is happening. And for example, here it's very explicit, right? Because if I look at to what terms or, what are the terms where I induce disorder? So, all these terms are affected by this disorder term, but not actually my scar. So this is very like a nice visualization of that. Okay, then you can play the same game with the other terms and so on. However, of course, the obvious remark is that here for simplicity we have been only focusing on one cluster sector. Also because to visualize higher number of clusters is difficult because you have your hypercube. It's not a planar thing anymore. And again, borrowing the picture, omnipresent picture in all many-body scar papers, if I plot entanglement entropy, I get my band of special states. And here, so these states would correspond to 0 number of clusters, 1 number of cluster, and so on. So this is again like a comment that this mapping holds for also different number of clusters. And the final comment is that it's also interesting actually to ask the question how this Hilbert space picture changes. It's a bit difficult to like visualize it. Nevertheless, you can do some simple combinatorics, which allows you to quantify somehow like the number of bulk states. Yeah, so in this picture, all these states sitting on the boundary would be boundary states, and all the rest will be bulk states. And the bulk states here are states which are actually characterized by like as maximum valency vertices of my graph. Yeah, so here the valency would be like 4, yeah, because I have 4 connections. And if you actually look at the boundary, so all the boundary states are states which have smaller valency. And this is kind of nice because by doing this combinatorics, what we actually find is that in the limit of vanishing filling fraction, like the ratio of like here, like the volume of the boundary is just the number of these boundary states, and the of bulk, and the volume of boundary is number of boundary states. And in the limit of vanishing filling fraction, the bulk is like essentially taking the whole of your Hilbert space. Yeah? So most of your Hilbert space is really indeed your like hypercubic lattice. On the other hand, if you go to the opposite limit of like half filling, you actually find that depending on parity of if you have even or odd number of spins, the volume of the bulk is not only constant, but it's like 1 or 2. Yeah, so like you really have like just 1 or 2 maximum valency like basis states, and like all the rest is, in the sense of this definition, a boundary of your Hilbert space. So with that, let me conclude. So under the facilitation condition, the positional disorder it has dramatic effect on the excitation dynamics. It is an opportunity, and I think a window to explore in more detail spin boson models, not only spin models. It's a great resource which provides a number of theoretical challenges. So for instance, how to actually describe this entangling dynamics between spins and bosons. And perhaps, okay, this might inspire some further applications, say to sensing and quantum information processing. So for example, you can think of what kind of like continuous variable states you can actually engineer with your atoms. And with that, thank you very much for your attention. And yeah, so if you have further questions.
Perfect. Thank you very much for this great talk. So we can stop the recording now so that people can ask questions.